Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. And today we're looking at lesson 2.2, which is on one-dimensional force type of problems. And in these kinds of problems, we will be looking at problems in one dimension in both the y direction. And these kinds of problems will concern things like elevators and air resistance, those to be in the y direction. The ones in the x direction, also one-dimensional. We will look at friction and multi-body types of problems. For today, we're just going to focus ourselves in the y direction with the elevator kinds of problems and problems involving air resistance. Friction and multi-body problems will be in another lesson. All right, so an elevator, and most of you have ridden an elevator, I'm sure. And so the basic forces that are acting on an elevator are essentially just two, where we have tension in a cable that is moving and holding the elevator in place. And we also have the force of gravity that acts down on the elevator. And what we're looking at with these kinds of problems is we're going to be looking at a mass that's inside the elevator. It could be a person or whatever it is, some kind of an object that has mass that's inside the elevator. And that's what we're interested in with these elevator types of problems. So what we'll do then is we'll look at these kinds of situations from the point of view of a Newton scale. So let's say somebody is standing in the elevator, and let's say that they're standing on a Newton scale, which actually measures their weight, not their mass, but actually measures their weight, which is their mass times the acceleration due to gravity. So when the elevator is just standing still and somebody were to stand on the scale, then obviously the scale reading would be equal to the force of gravity if they're not accelerating. And that we would call the normal force. And again, it's the same sort of thing as I am not going down to the first floor in this building because this floor is providing a normal force for me, which is equivalent to the force of gravity on me as well. So I am not moving or not accelerating in the y direction. So same sort of thing here. Somebody or an object is in the elevator and it's not moving, then the normal force provided by the elevator floor will equal the force of gravity on that object or the person. So in this situation then, obviously the tension in the cable, and these are usually steel cables on the elevators, the tension in the cable is going to equal the force of gravity if the elevator is not accelerating. And so that also means that as the tension force goes, so does the normal force. And so it's actually not that difficult to analyze if you recall, or if you just remember that there is that relationship between the tension in the cable and the normal force on the person. So let's say you step onto the elevator, and the elevator, you're on the ground floor and you want to go to a higher floor. The elevator will need to accelerate initially in the up direction, which means then that the tension force in the cables is going to increase. So the only way it can accelerate in the upward direction is if the cable force increases and becomes greater than the force of gravity. So that means then that the normal force also has to increase in order for you to accelerate in the upward direction with the elevator. Hopefully you move with the elevator. And so your normal force then will be greater than the force of gravity, just for that instant while the elevator is accelerating. And then when it reaches constant speed, fairly soon, then the forces will be equal again. The normal force will equal the force of gravity. Then let's say you're approaching your, so as I mentioned, the normal force then will be greater than the force of gravity. And so now let's say you're getting near the floor where you want to get off at, and the elevator is stopping. In this case now, in order to stop, the tension force in the cables have to be less than, or they decrease and will be less than the force of gravity, and hence the normal force will also decrease and will be less than the force of gravity just for that instant while the elevator is slowing down. And then it comes to a stop, and of course the normal force again will equal the force of gravity. So that describes a trip on an elevator when you're going to a higher floor. Now let's say you're starting at a certain floor. And then just mentioning here that the normal force will be less than the force of gravity. And in this situation, just while the elevator is stopping then, what's happening is your acceleration will actually be in the down direction now. So as the elevator goes up, when it accelerates you in the upward direction, you have acceleration up. As it comes to a stop, the acceleration is actually in the down direction for that instant while the elevator is stopping. Now let's look and see, let's say you're on an upper floor of a building and you want to go down to a lower floor. So you step on the elevator, and now in order for that to take place, the tension force has to decrease, which means the normal force on you also has to decrease. So what happens then is the normal force will have to be less than the force of gravity, and so you will start to accelerate in a downward direction. And very soon the elevator will be going at a constant speed, so once again the force of gravity is going to equal the normal force very soon. Then let's say you're getting close to the floor that you want to stop at and get off. And so what's going to happen there is that, I'll just back up 1 second here, yeah. As the elevator stops and it gets near the floor where you want to get off, then the tension force in the cable has to increase in order to slow the elevator down. So that means that the normal force on you will also increase, and so the normal force will be greater than the force of gravity, and your acceleration will be in the up direction in this case. And then you'll come to a stop, and then of course the normal force again will equal the force of gravity. So those are the essentials of the elevator problem. And next we'll just look at the airplane or the parachute type of a problem. And so let's say we have a person who decides to jump out of a perfectly good airplane. I'm not sure why somebody wants to do those kinds of things, but people do. And that's great if they want to do that. You probably won't ever find me doing that, however. So people do jump out of perfectly good airplanes. And quite often what they like to do is to just free fall for a while. So they jump out of a plane, and the only force acting on them is gravity, which means that they are indeed, by definition, in a free fall during that time. So during that time, they are accelerating in a downward direction, and because the motion is in a downward direction, the drag force just by the surface of the person, you will create a drag force in the up direction. So the drag force again is opposite the direction of motion, and so the drag force actually is proportional to the speed of the person. So the faster a person goes, the greater the drag force. And so you can actually write an equation like that, so that the drag force is going to equal some coefficient times the person's speed. And this number will vary depending upon the shape and size of the object, etc. It depends on a lot of factors. And so as their speed increases, the drag force will increase. And at a certain point then, the drag force then will equal the force of gravity. And when that happens, what we say is that the person has reached their terminal velocity in a free fall. All right, so now let's look at a different situation. Let's say a person jumps out of a perfectly good airplane and deploys their parachute immediately. So what happens then is you have the force of gravity acting in a downward direction. And once again, the acceleration is in the down direction, the motion is in the down direction, so you will have the drag force in the up direction. In this case, because of the size of the parachute, the drag force, or the coefficient, will be much larger. And so therefore, the number, the coefficient A, will be greater with the parachute than without a parachute. So what that means then is that the drag force is going to equal the force of gravity much sooner with a parachute. So that means that your terminal velocity will be less with a parachute than it will be without a parachute. And hopefully the terminal velocity with a parachute is of such a magnitude that you won't break any limbs as you hit the ground. That's the whole basis behind the parachute. So if we look at another situation, what a lot of people like to do is jump out of a perfectly good airplane, free fall for a while, reach the terminal velocity in a free fall, then deploy the parachute, and then they will reach the terminal velocity with the parachute. But this is a little bit different because, as we will see, when they first jump out of the plane in a free fall, their acceleration is in the down direction. They will reach the terminal velocity, at which point there's zero acceleration. Then, because their terminal velocity in a free fall without the parachute is going to be higher, when they do deploy their parachute, the acceleration will actually be in the up direction because it's slowing them down, which would be a good thing. And then they will reach their terminal velocity with the parachute, at which time the acceleration once again is zero. So a little bit of a different scenario, and be careful when you're analyzing a problem such as this that if you free fall for a while and then deploy your chute, you will actually get acceleration in the up direction because you're slowing down.